Today I have spent all my free time for my family, studying and workout. It's more than 10 o'clock and I will have a short talk. To be good at IELTS speaking test, you must be good at pronunciation and no matter your vocabulary. Okay, the topic is about black holes. Black holes are among the most destructive objects in the universe. Anything that gets too close to the central singularity of black holes, an asteroid, planet, or star, risks being torn apart by its extreme gravitational field. And if the approaching object happens to cross the black hole event horizon, it will disappear and never re-emerge, adding to the black hole's mass and expanding its radius in the process. There's nothing we could throw at the black holes that would do the least bit of damage to it. Even another black hole was destroyed, the two will simply merge into a larger black hole, releasing a bit of energy at the gravitational waves in the process. By some accounts, it's possible that the universe may eventually consist entirely of black holes in a very distant future, and yet there may be a way to destroy or evaporate these objects after all. If the theory is true, all we need to do is wait. In 1974, Stephen Hawking theorized a process that could lead a black hole to gradually lose mass. Hawking radiation, as it came to be known, is based on well-established phenomena called quantum fluctuation of the vacuum. According to quantum mechanics, a given point in spacetime fluctuates between multiple possible energy states. These fluctuations are due by the continuous creation and destruction of virtual particle pair, which consists of a particle and its oppositely charged antiparticle. Normally, the two collide and annihilate each other shortly after appearing, reserving the total energy. But what happens when they appear just at the edge of the black hole's event horizon? If they are positioned just right, one of the particles could escape the black hole's pull while its counterpart falls. It would then annihilate another oppositely charged particle within the event horizon of the black hole, reducing the black hole's mass. Meanwhile, to an outside observer, it would look like the black holes have emitted the escaped particle. Thus, unless a black hole continues to absorb additional matter and energy, it will evaporate particle by particle at an exhaustively slow rate. How slow? A branch of physics called black hole thermodynamics gives an answer. When everyday objects or celestial bodies release energy to the environment, we perceive that as heat and can use the energy emission to measure the temperature. Black holes and thermodynamics suggest that we can simply define the temperature of black holes. It theorized that the more massive of the black holes, the lower its temperature. The universe's large black holes would be of temperatures of the order of 10 to the 17th power of Kelvin, very close to absolute zero. Meanwhile, one of the mass of asteroid Vesta would have a temperature close to 200 degrees Celsius, thus releasing a lot of energy in the form of Hawking radiation to the cold outside environment. The smaller of the black holes, the hotter it seems to be burning, and the sooner it will burn out completely. Just how soon? Well, we don't hold our breath. First of all, most black holes accelerate or absorb matter and energy more quickly than they emit Hawking radiation. But if a black hole with a mass of Elson stops accelerating, it would take 10 to 67 power years, many magnitudes longer than the current age of the universe, to fully evaporate. When a black hole reaches about 230 meters ton, it will have only one more second to live. In that final second, its event horizon becomes increasingly tiny. until finally releasing all of its energy back into the universe. And why Hawking radiation has never been directly observed. Some scientists believe that certain gamma rays flash detected in the sky are actually just of the last moment of small predominant black holes forced in the dawn of time. Eventually, in an almost identified distant future, the universe may be left at a cold and dark place. But if Stephen Hawking was right, before that happens, the normally terrifying and otherwise impervious black holes will end their existence in a final blaze of glory. And this vlog